Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Classical Theory of Fields 2 from paper Classical Mechanics. So students, let us see what we are going to learn in this module. In this module, we will learn the Lagrangian formulation of the electromagnetic field. Secondly, we will learn about the gauge invariance of conservation laws of the electromagnetic field. We will learn to obtain the equations of motion of a relativistic particle in the gravitational field using the Lagrangian formalism. Historically, the concept of action at a distance was developed to explain the force experienced by a body in the presence of gravitation and electromagnetic forces. The concept of fields was later developed by Faraday and Maxwell to account for action at a distance experienced by a charged particle in the presence of other charged currents. Maxwell developed the theory of electromagnetic fields through Maxwell equations which accounted for all electromagnetic interactions including light. In Maxwell's theory, fields are physical entities. The Lagrangian and Hamiltonian formulation of electromagnetic fields was later developed. The quantization of electromagnetic fields was achieved by Werner Heisenberg, Wolfgang Pauli, and Paul Dirac, among others, to give the theory of quantum electrodynamics. The theory turned out to be the most accurate theory for the prediction of electromagnetic phenomena and predicted the existence of photons as light particles mediating electromagnetic interactions between charged particles. The theory of quantum electrodynamics has been tested to unprecedented accuracy to as much a 9 decimal points agreement between theory and experimental observation. It remains as the crowning glory of the success of quantum mechanics. We next discuss the electromagnetic fields. Maxwell equations relate electromagnetic field to charge and current densities. The equations are divergence of E is equal to rho and divergence of B is equal to 0. Now curl E is equal to minus del B by del T and curl B is equal to J plus del E by del T. Let us say these as equation 28.1. There are 6 components of electric and magnetic field, but they are related by Maxwell's equations. Del dot B equals 0 and del cross E equals minus del B by del T, of which there are 4 relations between the components of E and B. Del dot B is equal to 0 is one such equation. Curl E is equal to minus del B by del T is a set of 3 equations, one for each component. Thus, there are only 2 independent degrees of freedom. Since divergence of a curl of vector is always 0, so B can be written as curl A. The curl of a gradient of a scalar function is always 0. So E plus del A by del T can be written as minus del phi. The 6 components of electric and magnetic fields can thus be expressed in terms of 4 components of a 4 potential A mu defined as A mu is equal to phi A, which is equal to A naught comma A. We can now define an antisymmetric field tensor of rank 2 as F mu nu is equal to del mu A nu minus del nu A mu, which is equal to minus F nu mu. Now, F mu nu has 6 components. F0i is equal to del naught AI minus del I A naught, which is equal to del A by del T plus del operator on A naught, which is equal to minus EI. we have Fij is equal to del I Aj minus del J Ai, which is equal to minus del I Aj plus del J Ai, which is equal to minus epsilon Ijk Bk. Therefore, F mu nu is equal to a matrix with first row elements being 0 minus E1 minus E2 minus E3, second row being E1 0 minus B3 B2, third row being E2 B3 0 minus B1, fourth row being E3 minus B2 B1 and 0. The electromagnetic tensor F mu nu transforms as F prime mu nu is equal to lambda mu alpha into lambda nu beta into F alpha beta. Maxwell equations in terms of F mu nu are del mu F mu nu is equal to J nu, where J nu is a function of where rho and J. Del mu of F mu nu is equal to del mu of, within the brackets, del mu A nu minus del mu A mu, which is equal to the d'Alembert operator A nu minus del nu of del mu A mu, which is equal to J nu. The Maxwell's equation in terms of vector potential A mu can be written as del square by del T square minus del operator square within the brackets multiplied by A nu minus del nu into del mu A mu, which is equal to J nu. There is, however, a freedom in the choice of A mu without disturbing the Maxwell equation. We can make a transformation A mu tending to A prime mu, which equals A mu plus del mu of lambda x. The transformation does not change the field tensor F mu nu. F mu nu tends to F prime mu nu, which equals del mu into A prime nu minus del gamma of A prime mu, which equals del mu A nu minus del nu A mu, plus del mu lambda of x minus del mu lambda of x, which equals F mu nu. Thus, under the transformation del mu A mu tending to del mu A prime mu is equal to del mu A mu plus del mu lambda of x. This is equal to del mu A mu plus d'Alembert operator lambda of x. If we choose the scalar function lambda of x such that the d'Alembert of lambda of x is equal to minus del mu A mu, we have del mu A prime mu equals 0. But A mu and the transformed A prime mu give identical Maxwell's equation. So we can always choose del mu A mu equals 0. Let us call it as equation 28.12. This is called Lorentz gauge and it is a covariant gauge. This condition, if satisfied by the vector potential A mu, reduces the independent components of A mu from 4 to 3 and A mu is said to satisfy the Lorentz condition. Thus, as long as the scalar function lambda of x satisfies the condition, d'Alembert of lambda of x is equal to 0, Lorentz condition is satisfied. If we now choose the scalar function lambda of x to be del of lambda of x by del t equals minus pi, which is equal to minus a naught, we have since A prime mu is equal to A mu plus del mu of lambda of x. So we have phi prime naught is equal to A naught plus del lambda of x by del t equals phi plus del lambda of x by del t equals 0. And hence from del mu A mu equals 0, we have A naught equals phi equals 0, that is del dot A equals 0. The vector potential satisfies this extra condition and is said to satisfy the radiation Coulomb gauge. In this gauge, there are effectively two independent components of the vector potential mu. This is the physical gauge. We next study the Lagrangian formulation. We have at our disposal at second rank field tensor F mu nu and two 4 vector potential A mu and the current density J mu. We construct a Lorentz invariant scalar Lagrangian function which would result in the correct electromagnetic field equations. We write the Lagrangian density for the electromagnetic fields as Lagrangian is equal to minus 1 by 4 F mu nu contracted with F mu nu minus J mu A mu. The Euler-Lagrangian equations for A nu are given as del mu of delta L by del of del mu A nu minus delta L by del A nu equals 0, or delta L by del A nu equals J nu. Delta L by del of del nu is equal to minus 1 by 2 F alpha beta into delta F alpha beta by delta of del mu delta A nu, which equals minus 1 by 2 F alpha beta into delta of del alpha A beta minus del beta A alpha divided by del mu delta A nu. This equals minus 1 by 2 F alpha beta into, within the brackets, delta alpha mu into delta beta nu minus delta beta mu into delta alpha nu, which equals minus 1 by 2 into F mu nu minus F nu mu is equal to minus F mu nu. Here, we have used the fact that the mu and nu in equation 28.15 are dummy indices and F mu nu contracted with F mu nu is equal to, and contravariant F mu nu with the covariant component F mu nu is equal to the covariant component of F mu nu with the contravariant component of F mu nu, which accounts for a factor of 2. The Euler-Lagrangian equations given by equation 28.16 becomes del mu F mu nu equals J nu, or del mu of del mu A nu minus del mu A mu equals J nu, or I can say d'Alembert of A nu minus del mu of A mu equals J nu in the Lorentz gauge. In order to make transition from classical electrodynamics to quantum electrodynamics, it is convenient to add an extra term in the Lagrangian given by equation 28.15 called the gauge fixing term. So, L prime is equal to minus lambda by 2 into del mu A mu whole square summed over the entire mu. In the presence of this term, Lagrangian L is equal to minus 1 by 4 into F mu nu contracted with F mu nu minus lambda by 2 del mu A mu whole square minus J nu A mu. The corresponding Euler-Lagrangian equation can be obtained. As before, delta L by delta A nu is equal to J nu, and delta L by del of del mu A nu is equal to J nu now becomes delta L by del of del mu A nu is equal to minus of F mu nu minus lambda of del alpha A alpha into delta of del beta A beta by del of del mu A nu, which equals minus F mu nu minus lambda of del alpha A alpha into delta mu beta into G nu beta, and del mu of delta by delta del mu A nu equals minus of del mu into F mu nu minus lambda into del beta of del alpha A alpha. We thus have for the Euler-Lagrange equation d'Alembert of A nu is equal to 1 minus lambda into del nu of del mu A alpha, which equals J nu. In the Feynman gauge, lambda is equal to 1 and the Euler-Lagrangian equation becomes D'Alembert of A nu equals J nu. In free space with no charges and currents, the electromagnetic vector potential satisfies the D'Alembert of A mu equals 0, which is the equation of a massless vector field. The momentum conjugate to the field A mu is given by pi mu is equal to delta L by delta A mu. For Lagrangian L equals minus 1 by 4 into F mu nu contracted with F mu nu minus lambda by 2 into del mu A mu whole square summed over the all mu. So delta L by delta of del mu A nu is equal to minus of F mu nu minus lambda into G mu nu into del lambda into A lambda. Pi mu is equal to delta L by delta of del naught A mu, which equals minus F naught mu minus lambda G naught mu into del lambda A lambda, which equals del mu A naught minus del mu A mu minus lambda G naught mu into del lambda A lambda. Pi naught is equal to del naught A naught minus del naught A naught minus lambda into within the brackets del naught A naught minus del I AI, which equals minus lambda into A dot naught plus lambda into di AI, and pi I is equal to del I A naught minus del naught AI. In the Feynman gauge, lambda is equal to 1, so pi naught is equal to minus lambda dot I plus del I AI. Pi I is equal to minus lambda dot I plus del I A naught, and pi mu is equal to minus A dot mu plus del I A mu. The energy momentum tensor T mu nu is equal to delta L by delta of del mu A alpha into del mu A alpha minus Lagrangian of delta mu nu. By using the metric tensor, to raise and torr indices can be written as T mu nu is equal to delta L by delta del mu A alpha into del mu A alpha minus G mu nu L. For the electromagnetic Lagrangian in free space, we have Lagrangian L equals minus 1 by 4 into F eta sigma contracted with F eta sigma. So, delta L by delta of del mu A alpha is equal to minus 1 by 2 F eta sigma delta of del eta A sigma minus del sigma A eta with respect to del mu A alpha. This equals minus 1 by 2 into F eta sigma into within the brackets del mu eta minus del alpha sigma minus del mu sigma into del alpha eta, brackets close, which equals minus F mu alpha. Therefore, T mu nu is equal to minus of F mu alpha into del mu A alpha plus 1 by 4 into G mu nu into F alpha beta contracted with F alpha beta. The Lagrangian is not unique and neither is it gauge invariant. We can always add the 4 divergence of a vector without changing the action, and hence the equation of motion remains unchanged. Thus, adding a term del alpha F mu alpha A nu to the energy momentum tensor given in equation 28.28, we get T mu nu tends to minus F mu alpha into del nu A alpha plus del alpha into F mu alpha A nu plus 1 by 4 G mu nu F alpha beta contracted with F alpha beta. This equals minus F mu alpha into del nu A alpha plus F mu alpha into del alpha A nu plus del alpha F mu alpha A nu plus 1 by 4 G mu nu F alpha beta contracted with F alpha beta. This equals F mu alpha into within the brackets del alpha A nu minus del nu A alpha plus del alpha F mu alpha into A nu plus 1 by 4 G mu nu into F alpha beta contracted with F alpha beta is equal to T mu nu is equal to F mu alpha into F alpha beta into G mu nu plus 1 by 4 F alpha beta contracted with F alpha beta into G mu nu. Since del alpha F mu alpha is equal to 0 in the absence of free charges and currents, T00 is equal to F naught alpha into F alpha naught into G naught beta plus 1 by 4 F alpha beta contracted with F alpha beta G naught naught. This equals F naught alpha contracted with F alpha naught plus 1 by 4 F alpha beta contracted with F alpha beta, which equals E square minus B square by 2, and T naught naught is equal to E square plus B square divided by 2 is the energy density stored in the electric and magnetic fields. The electromagnetic momentum density is given by T naught I is equal to F naught alpha into F alpha beta into Gi beta plus 1 by 4 F alpha beta contracted with F alpha beta into G naught I. Thus, T naught I is equal to minus of F naught alpha into F alpha I, which equals the ith component of E cross B. This is the familiar Poynting vector S, which equals E cross B, and we recover the well-known Poynting theorem in charge and current free space. So we have minus d by dt into the integral E square minus B square by 2 d3x is equal to integral over ds dot E cross B. For the massive vector field, the Lagrangian density is given by Lagrangian L equals minus 1 by 4 F mu nu contracted with F mu nu plus 1 by 2 m square A mu contracted with A mu. The Lagrange's equation of motion is del mu into, within the brackets, del mu A nu minus del nu A mu, brackets close, plus m square A nu equals 0, or D'Alembert plus m square operator plus m square acting on A nu minus del mu A mu equals 0. If we choose del mu A mu equals 0, 4 components of massive vector field reduce into 3 independent components, and the equation of motion for the massive vector field becomes D'Alembert operator plus m square acting on A nu equals 0. Next we discuss the motion of a particle in the gravitational field. The action of a particle in special theory of relativity is given by S is equal to minus mc into integral over ds, where ds square is equal to g mu nu into dx mu into dx nu, and g mu nu is equal to 1 comma minus 1 comma minus 1 comma minus 1, and the equation of motion is obtained by extremizing the action S, that is delta S is equal to minus mc delta into integral of ds equals 0. In general theory of relativity, the matrix G mu nu is no longer constant and depends on the space-time coordinates. Thus, delta of ds square is equal to 2s into delta s, which equals delta of G mu nu into dx mu into dx nu, which equals dx nu into delta of G mu nu by delta x sigma into delta x sigma plus G mu nu into delta x mu by delta x sigma into delta x sigma dx nu plus G mu nu into dx mu into delta x nu by delta x sigma into delta x sigma. This can be simplified to have dx mu into dx nu into delta G mu nu by delta x sigma into delta x sigma plus G mu nu into delta mu sigma into delta x sigma into dx nu plus G mu nu into delta nu sigma into delta x sigma into dx mu. This equals, within the curly brackets, dx mu into dx nu into delta g mu nu by delta x sigma plus 2g nu sigma into dx nu brackets close into delta x sigma is equal to ds into delta ds. Therefore, delta s into integral delta ds is equal to minus mc into the integral within the brackets 1 by 2 dx mu by ds into dx nu by ds into delta g mu nu by delta x sigma into delta x sigma plus g nu sigma into dx nu by ds into delta x sigma by delta s brackets close into ds, which equals minus mc into the integral within the brackets 1 by 2 mu nu into delta g mu nu by delta x sigma into delta x sigma plus g nu sigma into mu nu into delta x sigma by delta s brackets close into ds. Integrating the second term by parts, we have the integral g nu sigma into mu nu into delta x sigma is equal to g nu sigma mu nu into delta x sigma minus the integral d by ds g nu sigma mu nu into delta x sigma. The first term vanishes at the endpoints, therefore we get delta s is equal to minus mc into integral 1 by 2 u mu into u nu into delta g mu nu by delta x sigma into delta x sigma minus d by ds of g nu sigma into u nu brackets close into delta x sigma ds, which equals minus mc into within the brackets integral of 1 by 2 u mu u nu into delta g mu nu by delta x sigma minus g nu sigma into du mu by ds minus del g nu sigma by del x into del x where rho by del s into mu nu brackets close into delta x sigma ds. The third term is curly brackets and can be written as minus del g nu sigma by del x rho into where rho u nu is equal to minus 1 by 2 u mu u nu into within the brackets del g mu sigma by del x nu plus del g nu sigma by del x mu. We thus get delta s is equal to minus mc into the integral 1 by 2 u mu u nu into within the brackets del g mu nu by del x sigma minus del g mu sigma by del x mu minus del g mu sigma by del x nu brackets close minus g nu sigma into d mu nu by ds brackets close into delta x sigma ds. Equating the coefficient of delta x sigma on both sides, equating the coefficient of delta x sigma, we obtain the equation of motion in a gravitational field as g mu sigma into d mu nu by ds plus gamma of sigma mu nu into u mu u nu equals 0, where the Christoffel symbol gamma sigma comma mu nu is gamma sigma comma mu nu is equal to 1 by 2 within the curly brackets del g mu sigma by del x nu plus del g nu sigma by del x mu minus del g mu nu by del x sigma. So students, let us summarize what we have learned in this module. The electromagnetic field Lagrangian requires the gauge fixing terms to reduce the redundant 4 degrees of freedom to the physical 2 degrees of freedom. Secondly, the electromagnetic field equation of motion is d-elevation a mu equals 0, which is appropriate for a massless vector field. The motion of a particle in the gravitational field is determined by the Christoffel symbol gamma sigma mu nu. Thank you students for your attention.